Today we want to do an example in Green's theorem, which we're going to think of as the fundamental theorem of calculus for double integrals. So this is taking place in R2. And what we have is a smooth vector field on a region R. And then we'll define the closed curve that defines the boundary of the region R oriented counterclockwise. That's our positive orientation, the same way that we do with the unit circle. The important thing here is that our function, I didn't mention this yesterday, probably should have, the function has to be defined everywhere in the region. So if the function has a hole, or sorry, if the vector field has a hole in the region, then different things can happen. This is in the same way if we have a function that has, say, a vertical asymptote that's undefined at a certain point. That's going to mess up our integrals. So we have to be wary of that. All right, but let's start with the easiest case where we have a smooth vector field, that just means it's defined everywhere and differentiable everywhere on the region. So we do have all the elements that we want for a fundamental theorem of calculus. When we integrate the derivative of a function over a set, we evaluate the function on the boundary of the set, and that's what we're doing in Green's theorem. In this case, the derivative of the function taking place in taking the role of derivative of the function is the scalar curl of the function. It's this combination of mixed partial derivative, or combination of partial derivatives, partial f2 with respect to x minus the partial f1 with respect to y. And taking the role of the function is our smooth vector field f. Our set that we're integrating our derivative, over which we're integrating our derivative, is this region in R2, and C is the boundary of that set going around in the positive direction, counterclockwise, our traditional positive direction. Counterclockwise, assuming that we're standing at the front of the clock. All right, so let's take a look, let's remind ourselves of some things. Remember that if f is a gradient field, then the scalar curl is going to be 0, and this whole thing gets very short because we got a closed curve. It starts and ends at the same point. And so if f is a gradient field, the fundamental theorem of calculus says evaluate the potential function at the endpoints. But if the endpoints are the same, then we're going to get 0. Also remember that if the scalar curl of a vector field is equal to 0, that means it's a gradient field. And so if we have a gradient field, then the scalar curl part is going to be 0. We integrate 0 over any region, and we'll get 0. So Green's theorem is specifically for line integrals that are not gradient fields. If we have a gradient field, then we just use the fundamental theorem of calculus for line integrals. So let's take a look at this vector field f, and we're going to go around the unit circle. This vector field is in fact a smooth vector field on the region that we're considering. We're going around the unit circle, so that's going to be our region. And I don't need to draw the unit circle, but I've been practicing drawing my circle. And this first quadrant is where I usually get squashed. That's a little bit better than normal. This one is definitely squashed. All right. That one came out pretty good. Pretty good for me. I know there are videos online of professors that can teach that can stand and draw like these perfect unit circles standing at the board. I cannot do that at all. I get distracted about partway through and then like cut a corner, and it's bad. So our region R is going to be everything inside. So there's our region R, and C is going to be the boundary. First thing that we want to notice that when we're thinking about this line integral is that we want to check if the function is a gradient field. If f is a gradient field, then this problem is going to be really short. We know we're going to get 0. So if the vector field is a gradient field, then the fundamental theorem of calculus, the line integral, will tell us that the line integral is going to be equal to 0, since C is a closed curve. The start point and end point are the same. No matter where we start, no matter where we end, we'll get 0. So we can check if the vector field is a gradient field by looking at the scalar curl. So F1, just using this notation up here, F1 of xy is equal to y, and F2 of xy is equal to negative x. So if we take the partial of F2 with respect to x, so we're going to check if it's a gradient field. The partial of F2 with respect to x is equal to negative 1, and the partial of F1 with respect to y is equal to 1. The scalar curl is not 0, therefore f is not a gradient field, so the fundamental theorem of calculus does not apply. This doesn't mean that we won't get 0. This just means that we're not going to get to 0 using the fundamental theorem of calculus for line integral. What we can do in this scenario is evaluate the line integral using Green's theorem. So we can't use the fundamental theorem of calculus for line integrals, but we can use Green's theorem because this fits the requirements for Green's theorem, obviously, because this is when we're talking about Green's theorem. So we can use Green's theorem to calculate the line integral. So what I mean when we're going to use Green's theorem to calculate the line integral is that we're going to calculate the double integral over the region contained by the curve C. So we're going to be doing this part, this integral Now we're going to we need to set up a double integral. And this is just a double integral over a unit circle. So we need to set up a double integral. So I need to describe the x's and the y's. It's a unit circle. So I'll send the x from -1 to 1. And then we can integrate y from a negative square root to a positive square root. Our scalar curl, partial f2 with respect to x minus partial f1 with respect to y, is just going to be a -1 minus 1. And I've set this up as a dy dx integral. So we're just integrating a -2. Any questions? Anyone foresee any problems that I've got coming up? Look into the future. See any problems? Any flaws in my strategy? Is everybody okay with this strategy? Let's proceed and find out. So we've set up this double integral. We just need to integrate the function -2 with respect to y. So this function in here is just a -2. That's nice and easy to integrate. So we're going to be integrating from -1 to 1, -2y evaluated from the negative square root to the positive square root. This is still in an integral dx, and x is going to go from -1 to 1. So I got a -2 times the square root minus a -2 times the negative square root. Assuming I'm doing my calculations correctly, which is not a safe assumption. We just need to know how many square roots we're going to be dealing with. So we are subtracting because it's f at b minus f at a. And so we're subtracting, but it's minus a -2, so it's plus. And then this is a negative because that's the one we're plugging in down here. That saved us from having just 0 here. Which one? This one? No, it's a negative. We're plugging it. We have a -2. No, plugging it. That's okay. Dropping a negative is totally something I would absolutely do, especially at this time in the morning. Always watch me carefully when I'm doing calculations. Especially when I know I'm going to bail on the calculation pretty soon because we just ran into what I don't like about this particular integral that I've set up. Yeah. And the other problem is that I don't remember what this antiderivative is. So does anybody remember what this one is? What's our strategy for when we don't want to do trigonometric substitution? The strategy for avoiding trigonometric substitution is not to do the trigonometric substitution here, where it's going to be a lot of work. Back up, do the trigonometric substitution up here by doing the whole integral in polar coordinates. This was the problem that I was alluding to earlier. I've got a round thing and I'm here describing it with rectangular coordinates. So we're making our lives difficult. So don't do trigonometric substitution here. Do it back here. That way the entire class, when they're taking notes, like, oh, dude, why didn't you say that earlier? Why did we have to write this down? And and the answer is because I'm a cruel taskmaster that makes you want to think about trigonometric substitution just because it's my favorite method of integration. So at this point, we'd be like, oh, ew, trig sub. Oops. And we're all sad about that. But then we're going to be smart. And instead of doing trig sub now, let's go back in time and do the trig sub here. Yeah, ran out of space. Instead of doing the trigonometric substitution now in our dx integral, let's go back and rewrite this as an r and a theta and integrate then, because all I want is the I want this double integral of this function, and that function is just a -2. If that function had x's and y's in it, I'd have to translate those into r's and theta, but we have ways of translating those into r's and theta. So we're going to rewind. So our scalar curl was just -2. That doesn't change. But now when I set up the double integral, we're going around the unit circle. I can integrate r from 0 to 1 because it's the unit circle. And since it's polar coordinates, we'll just integrate theta from 0 to 2 pi. Because in polar coordinates, a circle is just 2 intervals. -2 is what we're still integrating. And remember that dA in polar coordinates is not just dr and d theta. D theta is not a length. We need to multiply by r to turn d theta into a length. So I need an r d theta dr. So we integrate with respect to theta. So we'll get -2 r theta. Evaluate from 0 to 2 pi. This is still an integral dr from 0 to 1. We plug the 2 pi into theta and then the 0 into theta. So 2r times 2 pi is -4 pi r. Then when we plug in 0, we get 0. And we still need to integrate dr. The integral of negative 4 pi r is negative 2 pi r squared. And we'll evaluate from 0 to 1. So by Green's theorem, the integral around C of f dot dr is also equal to negative 2 pi. If you want to think of this in terms of a line integral, we have to set up a parameterization for our circle. And now we can see why I use the unit circle, because the parameterization is nice and simple. So if we want to set this up as a line integral, we'll have to parameterize our curve. And so our line integral, the integral around C of f dot dr, we're going to integrate from 0 to 2 pi because we are now parameterized. F evaluated at r is going to be yi, so the y is sine of t, so sine of t minus the x, which is cosine of t, remember, I'm not just integrating the parameterization, I'm integrating the vector field evaluated at the parameterization. So here, this is indicating that x of t is cosine t and y of t is sine of t. That's why it looks backwards, but that's why it's only partially read, because I'm plugging cosine for x. So negative from the vector field, x is cosine of t times j. So I'm not just writing the parameterization. This is the disadvantage of using this one, but I didn't want to square the x or the y. And then I'll have the dot product with r prime, which is minus sine of t I plus cosine of t j dt. So our integral will still go from 0 to 2 pi. Sorry, 0 to pi, 2 pi. And we'll have minus sine squared minus cosine squared dt. Not surprised by this, we're finding a dot product. The dot product is a scalar product. So we're not surprised that we ended up with a scalar function. So we're just integrating the function -1 from 0 to 2 pi. Remember that the point of the problem was not to land on -2 pi. The actual calculation wasn't the point. The point was that we got -2 pi both ways, demonstrating an example of Green's theorem by calculating a line integral using a double integral. And first wanted to make sure that Green's theorem is appropriate because we wanted to make sure that we did not have a gradient field. If we have a gradient field, then calculating a line integral should be done with the fundamental theorem of calculus for line integrals. Any questions? How's everybody okay? Yes. The point of doing both was to show that both the double integral and the line integral come out to -2 pi. Yeah, so the idea is that we want to calculate a line integral. So we want to calculate a line integral for whatever reason. And if f is a gradient field, then we'll use the fundamental theorem of calculus for line integrals. That's one of the things that could happen. So if f is gradient field, if I don't know why I'm shouting, but if f is a gradient field, then we'll use the fundamental theorem of calculus for line integrals. If f is not a gradient field, and f is, and there's a lot of extra caveats for Green's theorem. If f is not a gradient field, and the curve is a simple closed curve enclosing a region in R2, then we can use Green's theorem. So if f is not a gradient field and C is the boundary of some region R and f is smooth on that boundary, then we'll use Green's theorem, which is the fundamental theorem of calculus for double integrals. So f is either a gradient field or it is not a gradient field. Now, if f is not a gradient field and we're in R3, then we have to do something else. You either have to calculate the whole thing directly or use some other as yet undiscovered theorem. Taking two partial, kind of combining the two partial derivatives. and then using and just calculating a double integral. So we're calculating a double integral, so we're using the fundamental theorem of calculus twice, once for the dx and once for the dy, or as we did it, once for the d theta and once for the dr. So doing both calculations is specifically because we wanted to demonstrate that that Green's theorem is going to that the double integral and the line integral will give us the same value. It doesn't look like a lot of savings in this case, specifically because our line integral was so simple to calculate. But this is because it's early and I did not want to make life difficult for myself because I didn't want to integrate sine cubed. Although that would have been a nice opportunity to do a substitute. Oh well. Sometimes we miss the opportunity. If I had put like a y squared I minus xj, or like a y squared xi minus x cubed j, like I do on the final, I'm just kidding. That would be a lot of work. Remember, every time y'all have to do one problem, I have to do that problem like 40 times. So that's the calculus of assigning problems for tests. Any questions? So an important thing to note about the particular calculation, I know we spent today like doing a calculation. The important thing to remember about calculations is that when you're in a math class, the end result is almost never the point of the problem. In your other classes, like in physics, you know, it might be the point of the problem to get at the number so that you can understand how certain things are interacting. I don't know. That's like physics stuff. What am I supposed to know about physics? Or even stranger, chemistry. Really, I just raid other subjects for things that we have to multiply. So I like grab the physics books, like, well, hey, what do you guys multiply over here? Oh, distance equal rate times time. That sounds pretty good. Work is equal to force times distance. That sounds pretty good. What if those things are at an angle? Oh, then we have to break into components. Oh, heck yes. I'm going to use that in line integral. And then the physics people will be like, well, oh, do you want a proper explanation for work? I'm like, well, hell no. Work is equal to force dot distance. I got what I need. They're like, you don't really understand what's going on. I'm like, got what I need. And I'm just walking out with my dot product. Then I come in here, and if you're really unfortunate, you're taking this class before you've talked about physics, and you get my explanation for what work is. Then you get to physics, like, well, this is not what's supposed to happen. But by this time, you've been through Calc 3, so I only run into you in the halls, and you're trying to avoid me anyway. So it all works out perfectly. You just have to deal with my shitty physics explanations. Anyway, that's going to do it for today. We want to talk more about some more different fundamental theorems of calculus. We got to set up some different kinds of integrals. There's still going to be dot products, so don't be surprised. That's it for today. I'll see y'all on tomorrow. Everybody have a good day. Thanks for playing.